One of the new features in 5G is the use of millimeter wave bands for communications to mobile phones. This is a prototype of a millimeter wave transmitter for the N257 band that spans between 26.5 GHz to 29.5 GHz. This is where the wavelength is roughly 10 millimeters, which is why the millimeter wave band typically is said to start there. What you can see is that it contains 16 different antenna elements in a square pattern like this. Each of these elements has an antenna gain of roughly 3 dBi, which means that it is radiating 3 dB or 2 times more power in this direction than an isotropic antenna would do. In total, when you have 16 antenna elements like this, it can create a directive signal forward towards you that will be 12 dB in addition to this 3 dBi antenna gain, so 15 dBi gain. So that means that it's much stronger in a particular direction than it would be with an isotropic antenna that sends out signals equally strong in all directions. And this is something that is important in millimeter wave communications in particular, because you need to use beamforming, directivity, to reach your receiver with sufficient signal strength. In this video, I will show you some of the basic benefits and features of having multiple antennas at the transmitter by using this developer kit from TMYTEK, which have a transmitter with 16 antenna elements, and 30 centimeters away we have a single receive antenna, which is connected to a 20 dB power amplifier, which is then connected to the receiving unit that measures the signal strength. And we need this power amplifier because already at the 30 centimeters distance, the received signal power is very weak. Even if there is 16 antenna elements, there's actually only 4 inputs to them. And this tells us that we actually only have 4 antenna dimensions. The first 4 elements in the first column is having the same input. The second column have the signal from the second input, the third column from the third input, and the fourth column from the fourth input. In later videos, we will send different signals or delayed versions of the same signal from these 4 different inputs, and that would allow us to control the directivity of the transmitted signal in the horizontal plane. In this video, we only want the signal to reach this receiver, and we will look at how directive it can become. Directivity is often illustrated as a beam like this. And when we're sending the same signal from all of these 4 inputs at the same time, then the signal is directive straight out of the array, perpendicularly. So we will have to rotate the transmitter in order for the directivity to point exactly towards our receiver. We will see that how directive the signal becomes depends on if we are transmitting from 1, 2, or all 4 of the inputs. The experimental setup contains 6 different components. There is a signal generator that is generating a sinusoidal signal at the carrier frequency that we are using, which is 26.5 GHz. Then it feeds this to the beamforming unit that is having these 4 input signals. So there is power amplifiers in all of these ones, and also the capability of phase shifting the signals, so you will have different delays of them when they are entering the antenna array. And every column can send a different signal in this antenna array. But we call these 4 antennas because there's only 4 inputs. Then the signal goes over the air to the receive antenna. The receive antenna is connected to a power amplifier that is amplifying it before we detect the resulting signal power at the power detector. The signal strength is varying between all of these different devices. If we start at the right-hand side, the signal generator is creating our millimeter wave signal at a certain signal power level. And then when it goes through the cable to the beamforming unit, we are losing a little bit. But the beamforming unit has power amplifiers, so we increase the signal power. And then that signal power is fed to the antenna array, which is creating a directivity. So even if it's not increasing the signal power, it is effectively generating a stronger signal in the direction towards the receiver. Then over there, we have what is known as the path loss. So with the distance, the signal is spreading out very quickly. So it's much weaker at the receive antenna than at the transmit antenna array. In the cable between the receive antenna and the amplifier, there is also further losses, but we have a 20 dB, so 100 times increase in the signal power before it is going to the power detector. And the important reasons of having an amplifier at the receiver is that you need to make sure that the received power in the power detector is much above the sensitivity level, the lowest level that the power detector can actually detect. There are two things that we will be varying in this video. One is the total transmit power, which will depend on how many of these 4 inputs that we are actually using for transmission. And the second thing is that when we are choosing to only use some of these 4 inputs, the gain or the directivity of this antenna array also varies. If we start with the reference case when only one of the inputs is active, and that is feeding its signal to one of the columns, well then we use a certain transmit power, and that transmit power is fed to the array, which is generating a gain towards the receive antenna of 9 dBi, meaning that you have a 8 times stronger signal pointing towards the receive antenna as if you would transmit isotropically. So it would seem like we are transmitting with 8 times more power than we're actually doing from the perspective of the receive antenna. But we are not generating more power, we're just directing it. Then when we are turning on additional inputs here, we also call them channels, then we are increasing the transmit power in total because each one of these ones have a power amplifier in its own. I have noted experimentally that the total transmit power is increasing by 2.5 times when I'm turning on all of these 4 inputs. It could have been 4 times larger, but it's not when we use this device. And then that power is reaching the antenna array where we get further directivity when we use all of the 4 antenna inputs. It generates a 4 times stronger directivity in that case. So 4 times 2.5, that's 10 times more. So we actually get a 10 times stronger signal when we use all 4 of the inputs compared to when we're only using 1. I have borrowed this experimental setup from TMYTEK, and you can find a link in the description with all the information about their product. And what you can see on the screen now is the software that is delivered together with it. On the left-hand side, you can see the received signal power in the 26.5 GHz band, and it's currently minus 30 dBm, which stands for decibels of milliwatt. So minus 30 dBm, that is 1,000 part of a milliwatt. So that is a very low received power. We achieve this by only transmitting from the first channel, meaning that we are transmitting from one column using what is essentially one transmit antenna. And we can increase the received power by turning on the second channel or the second column in our antenna array, and this will lead to an increased power because of 2 reasons. First of all, we are increasing the directivity. We are doubling that one because we are doubling the number of antennas we're using. And second of all, each of these antennas is connected to its own power amplifier, so we are also increasing the signal power that we are transmitting. The received signal power should increase by 3 dB thanks to the doubling of the directivity, and another few dB thanks for the increased transmit power. And we see that it increases with 4.5 dB, which means that the increased signal power is roughly 1.5 dB or 1.5 times the power. There are other practical reasons for not getting exactly the same received power level as the theory is telling us. One is that these computations that I was making is actually for a free space line of sight scenario where you see the receiver from the transmitter but there's no object around us. Here we have objects. If I now turn on the last 2 channels, so I use all of the antenna elements in my array, I will once again double the directivity, so I should get 3 dB from that in improvement in received power. And I'm also increasing the transmit power once again. So what will I get now? It's increasing to minus 20 dBm. So in total, we went from minus 30 dBm to minus 20 dBm. So that is a 10 times or 10 dB improvement, whereof 4 times comes from the beamforming directivity and another 2.5 times comes from the increased transmit power. So what did we learn from this experiment? Well, by using an array of antennas, we can get more signal power over a wireless channel. So when we were going from 1 to 4 transmit antenna channels here, we were getting not only 4 times more transmit power, but another 4 times more directivity. So we were focusing the signal towards the receiver. Under ideal circumstances, this should be 4 times 4, so 16 times stronger signal, which is called 12 dB. We only observed a 10 dB improvement when using this hardware because its maximum power is only 2.5 times that of one antenna, not 4 times. In the next video, we will have a look at how we can use the same setup to measure how the signal strength varies with distance and how different objects are blocking millimeter wave signals.